Okay, this set of notes, it's not really an example problem, but just a general scenario of what we went over in class, just to review it again on your own if needed. And it's working with Newton's second law, F net equals ma, on a pulley system, which is often referred to as an Atwood machine. And what a pulley system always does, whether it be just a simple one with two masses hanging off like this or a modified one we'll see in class later, is number one, the pulley changes direction of the system moving. So you can see we have a mass 1 and a mass 2 hanging off our pulley system, and as that thing goes into motion, if we call up the positive direction on this one, we will continue to take the positive direction over and around the pulley. So what up is the positive direction on mass 1, however down will be the positive direction on mass 2 as it goes around that pulley. We're going to be consistent with that, so it's something probably a little different we haven't ran into before. Alright, and an important note I put beside here with the star on it, because anytime, it doesn't necessarily have to be an Atwood machine, but anytime we solve a dynamics problem with Newton's second law that has multiple masses connected, we really should make a free body diagram for each of them, then identify an equation using Newton's second law for each of those two masses separately, and after that we'll make equal connections, as you'll see. This is a general scenario, no exact numbers, but how we would just set up in general two separate equations and then notice their relationships between them once we're done. So first we're going to just pull out mass 1 and only look at what forces are acting on mass 1. And on mass 1, since I drew the positive revolving clockwise around the pulley, up is positive for the tension pulling up on mass 1, and the weight of mass 1, always pointing down, is in the negative direction. Similar to that, we come over and draw the free body diagram for mass 2. Mass 2, though, this time up is in the negative direction, and down is in the defined positive direction, so we're going to keep that positive around the pulley consistent. We're not going to flip-flop it when we get over to the other side. Alright, now I'm going to, in green on each of these ones, just build an equation for Newton's second law, summing up all the forces on mass 1, and that would be tension 1 minus weight 1 is equal to ma. Similar up here, but remember the direction kind of got flip-flopped because of the pulley. We will have weight of mass 2 minus tension 2 equal ma. And what we have now is a system of two equations, but we have some similarities between the two, and we're going to note them in blue. And basically, if you don't make these connections after getting these two formulas, you'll probably have a tough time solving any problems that involve something like this. And let's even make sure we put mass 2 acceleration 2, mass 1 acceleration 1. Alright, number one thing that should be obvious and common sense is that these two masses, even though we built two different formulas for them, they equal ma by just definition of Newton's second law. But if you think about it, these two objects are connected with a rope. They're together. Therefore, it would only make sense that acceleration 1 from this equation has to equal acceleration 2 from the other equation. If two things connected had different accelerations, well, they're not really connected anymore, are they? So we could interchange A1 and A2, or if you would like, just call each one of them A at this point, because they're the same one. You don't have to differentiate them 1 and 2 anymore once we realize that. Alright, secondly, that it's just really as important, and this feature hinges on the fact that we're told to ignore friction. Probably won't be any time soon where we will have an Atwood machine where we don't ignore friction, so we'll only go over this scenario right now. If it says ignore friction in the pulley, that means the pulley itself on its axle has no significant friction, and the rope going over the pulley itself is creating no significant friction as well, we have another connection. That if that's the case, the tension in this rope magnitude will be the same magnitude as the tension in this rope. Their directions, remember when we built the formulas, were opposite because of the nature of the pulley's directional change, but their overall magnitudes, T1 and T2, will be the same. And that means, again, if we want to, we could get rid of the 2 and the 1 and just call them each generically tension because they equal the same thing. And what we have then is two equations we built with Newton's second law after making these connections right here that allow us to solve for really any unknown using a system. We have two equations where we're guaranteed the acceleration is the same value in both of those, and the tension is the same in both of those. So we could figure out any unknowns involved for whatever problem asks us, but those are the main connections you want to make with a simple Atwood machine when ignoring friction in the pulley itself.